Okay, so let's begin. Um, okay, so last week, what we did was we wanted to understand the field of NLP and gave some emphasis on large language models because a lot of people are saying that today using large language models. Okay, so this was deep neural networks. Now transformer, and now of course it is large language models and generative AI, which is the paradigm. So last week we mentioned the Turing test and Chinese room experiment as foundational to the question of AI itself. Can we say that a machine is intelligent? Can we say the machine has consciousness? Okay. Now that was a very fundamental point which we discussed. Then we looked at the definition of NLP, which is art, science, and technique of both natural language understanding and natural language generation. We also understood that NLP is a combination of language science and data science, the other name for which is linguistics and probability. We will see more of probability and its influence on NLP tasks like part-of-speech tagging, which will start today. And we also took a deep look at what do LLMs do after all. Okay, please don't talk. Please don't talk. Okay, what do LLMs do after all? LLMs essentially do prediction of next language object or properties of the input language object. Okay, so the prediction is the task of LLM. Like any model, for any model, the main task is prediction. Then we had this interesting observation that compared to humans, LLMs are extremely expensive in terms of size, the energy they consume, and also the carbon footprint that they leave in terms of polluting the environment. Of course, there are some caveats there which need to be addressed. LLM is maybe one machine, but human beings are millions, billions. So what about the collective, pollution caused by human beings? What about the collective energy consumed by all human beings? So there is a caveat there, but we saw that the energy requirement of an LLM compared to a human being is about 10,000 times. Okay, and the pollution that is caused is about 100 times by an LLM compared to a single individual. Now, we also described well-known large language models, medium language models, and small language models. Now, I forgot to point to one interesting observation to you that many of these small and medium language models are 7 billion parameters. Okay, the number of parameters being seven seems to be common across many language models. Now, towards the end of the class, we went to natural language stack. Okay, so this is what was done last week, and now we would like to get into more nitty-gritty questions, the question of part-of-speech tagging, for example. But before that, let me make some announcements. One is with respect to your assignment. This is the assignment plan. You can see it in your in the slides that will be uploaded. We will also put it up on Teams and Moodle. So the assignment plan is as follows. You have 3 assignments to do. Okay, and it is possible that many of you will be finishing these assignments in no time. But these assignments are extremely instructive with respect to the understanding of how data plays an important role for natural language processing. Okay, so in the early days of natural language processing, it was rule-driven natural language processing. A human being would sit down, understand the task, understand language phenomena, and then give rules. But this was not going very far. Okay, the systems which were created were very low, very high precision, but low recall. They would fail for any new situation, new example. So that was caused by lack of robustness. Now, robustness came because of the arrival of huge amount of data And NLP, how NLP makes use of data is very well illustrated by these assignments. And these assignments are chosen for a purpose. The first assignment is you'll have to do part-of-speech tagging using hidden Markov model. I will describe a large number of sources from where you can get the data, part-of-speech tag data. Of course, for the assignment, all of you will have to use only one data source. But you can make use of data from the divergent sources to make the training of the machine learning model very extensive and robust. Okay, so I'll give you a list of the places where you can get part-of-speech tag data. So the first assignment is hidden Markov model-based part-of-speech tagging, and also conditional random field based part-of-speech tagging. The theory of these algorithms, hidden Markov model will be started today, and conditional random field also will be described as we move forward, maybe half a lecture or one lecture. But once you implement them, your grip on these algorithms will be very robust, I would say. And you'll also understand why these machine learning algorithms have been successful for solving natural language processing tasks. So first is part-of-speech tagging using hidden Markov model and conditional random field-based model. That will be due end of August. End of September, after you finish this part-of-speech tagging, end of September, you will use support vector machine-based named entity identifier and also logistic regression-based named entity identifier. So, okay, before that, the example from part-of-speech tagging is if the input sentence is people laugh, then the output would be NN and VB, where NN means a verb, VB means a basic verb, okay, a verb in base form. So people laugh, output is NN, VB. For the second assignment, it is a binary classification problem. For every entity in the input sequence, you will have to decide if that entity is a name or not. Okay, for example, if the same sentence is taken, John laughs, the output should be 1, 0, because John is a name, laugh is not a name. Okay, so it's a binary classification problem. You will be using support vector machine for this and logistic regression also. These two algorithms also I will mention, but most probably you have done this in other courses or you'll be doing it in foundation of machine learning course. Okay, so the two algorithms are SPM and logistic regression. This should be due end of September. End of October, you will have to do transliteration from Indian language to English, and you'll have to do a statistical. You have to take a statistical approach. Which approach you take depends on you. You can make use of some aligner, for example. There are aligners like Berkeley aligner, then Moses aligner. Okay, it is up to you. You are also free to use encoder decoder network. I don't mind, but the task is this: you will have to take any Indian language of your choice and give the corresponding English string. So Mumbai written in Devanagari is output as MUMBAI, which is the Roman representation. Then Mumbai written in Tamil, again the output is Mumbai. If the problem seems trivial to you, you will have to take another look at it. There are lots of subtleties involved in the transliteration process, okay, because the same grapheme, the characters are called graphemes. Same grapheme does not map to the same phoneme. Phoneme is a sound element. Grapheme is a written character element. Phoneme is a sound element. So grapheme to character mapping is not always one-to-one. Okay, there ambiguity is possible. Okay, so for example, GUT is gut, right? Gut feeling, but PUT is put, right? So same grapheme has two different sounds, and that sound has to be captured in the target language string. When I write put in Hindi, I'll say pa, ukar, and ta. But if I write gut, GUT gut, I'll say ga, a ki matra, and ta. Okay, so depending on the pronunciation, the output string will change. So here I'd like to digress a bit and tell you something very interesting. So since transliteration is concerned with capturing the sound content of a string, there was a thought, why not go into the sound representation first of the grapheme string, and then from the sound representation, which is phonemic representation, go into the grapheme representation of the target language. Okay, so capture the sound content in Mumbai in Devanagari, and then transmit it into English, where the elements given to you are Roman characters. Okay, so this was the approach, and it was very intuitive, but it failed. Okay, what succeeded quite spectacularly is direct mapping of character to character. Okay, why could this be? This was a very strong empirical observation. What do you think could be the reason? Yeah.
Same word is spelled differently in many parts of the world because they have a certain accent. Then they would say difference in the phone.
That is the reason.
Causes the problems with
As opposed to direct transfer. So the question is, as opposed to direct mapping from character to character, that's grapheme to grapheme. If you take the grapheme phoneme grapheme approach, the two-stage approach, why is it that the two-stage approach performs lower than the single-stage approach?
Some speech sound is similar to another speech sound.
Mm-hmm.
There are some classes of consonants, we will say, where the sound is similar to each other. So that's where maybe.
No, that is not the reason. Yes.
Like a single mapping now, and that's how we have more chance for error.
What is it called? If you have a pipeline approach, yeah.
there would be less number of variations or less number of grapheme translation conversions that would be possible.
Yeah, so all the three answers are close to this, but the very simple answer is it is, shall I call it a law in machine learning, that whenever you have staged processing, every stage introduces its own error, and errors get multiplied. Okay, so grapheme to phoneme, if the accuracy is 0.7, phoneme to grapheme is 0.8, the overall accuracy is 0.56. Very low. Okay, so whenever we use a staged pipeline approach in machine learning, we have to be aware of the fact that we are introducing a multiplying effect, okay, multiplication effect in terms of error. Okay, so that was the digression. So here, I would suggest that you take a direct mapping approach of transliteration and choose any language you are comfortable with. Preferably choose your own mother tongue. Okay, because then you will have an intuition about the problem, and you will be able to do the error analysis much more effectively. Okay, so these are the three problems. All the three problems are very well tried out, umpteen number of papers, literature, but only one request is that do not borrow anybody's code. Do not download some code from Papers with Code or GitHub and use it. Please don't do that. We have mechanism to find out if you are using somebody else's code or you are doing it yourself. Also, don't ask an LLM to generate the code for you. Okay, so so all these, all these checks and balances will have to put in place. Do it by your own labor. You will get an insight into NLP. Okay, that is the benefit that you will derive from doing these three assignments. So the timeline is very clear. Okay, keep working towards it, and maybe some of you will finish this in 1 week, 2 weeks. I'll not be surprised. But these are very standard, very instructive assignments, and all the class size is about 400. Okay, and I don't know how many will continue. And we have decided that the group size for all assignments and projects will be 4. Okay, so 4 people will work on these 3 assignments. Also, do not please decide that I will do HML, you do SVM, and the third person does transliteration. Please do not have this kind of division of labor. We'll have a vibe continuously. And if you do not have insight into the problem, if you do not have insight into the code and implementation, you will lose a lot of marks. Okay, the penalty will be heavy. I want you, all of you, to do these experiments with full involvement. Do this assignment. And if you want some information on Indian language transliteration, we have a paper. Okay, and that has pretty impressive accuracy for different Indian languages. So you can take a look at this. And the last line is important. You must compare performance with chatgpt. These days, all NLP systems are required to give their performance vis-a-vis the performance of the chatgpt. Okay, that also you will have to do. You will most probably be surprised to see that Tamil to English transliteration is done very well by ChatGPT. Maybe. Okay, try it and see. But you will have to give the performance figure with respect to ChatGPT also. So this was for assignment. An assignment plan is completely in place, unlike the previous years. Any question on assignment? Yeah. Compare the performance of which by inspection. Yeah. Take 100 instances and give the figure. Okay. All. Then the project plan. Now, while assignments will clear your fundamentals, the project plan is at least we think should test your creativity and your ambitious approach to research. So project should be ambitious. The core should be 1 paper. Okay, so your project should have a very clear aim, and that aim possibly has been addressed by some existing work. That will be the case most of the time. But you are also welcome to suggest a completely novel project which nobody has done before. Okay, and which you think is worth doing. In fact, any problem in NLP is worth doing. So you are welcome to come up with your own idea, but guard against one possibility. Many times, young researchers come running with a lot of enthusiasm that this is an earth-shaking idea. Nobody has done this before. But make sure you have done your literature search very assiduously and meticulously. Okay, many times this happens. You think that nobody has done this before, but on very careful search for literature, you find that yes, somebody has taken that path. And for that, I would request that you go to papers with code, Google Scholar, Semantic Scholar, do a very, very meticulous and diligent search on the literature that exists. Okay, but nobody is saying that you have to come up with something which is absolutely new. You are welcome to implement 1 paper, 1 core paper. And of course, you should add something of your own to that idea. Okay, so the possible directions are multimodal emotion recognition, which is very important these days. Okay, then mental health monitoring using NLP, again important. Multimodal metaphors, simile, hyperbole. These are figures of speech, and chatbots are increasingly required to be intelligent with respect to human conversation. They should understand sarcasm, for example, or metaphor. So this is another direction. Language mixed question answering. Language mixed question answering. No, this is language mixed dialogue. Okay, so I'm carrying out the dialogue with a chatbot, and I mix language freely. This is also called code mixing, but I'm calling it language mixing. Okay, it is not only English, sometimes Hindi, sometimes English, sometimes Bengali, sometimes Marathi, all kinds of languages. It's a challenging problem. In a multilingual country like India, this is a very relevant problem. Then this is my favorite, and I think every year some students work on this project. OCR to machine translation to TTS pipeline. So you go to a foreign country, you do not understand the language there. You take the picture of some notice or announcement which you want to understand. So OCR converts this to text. That text gets automatically translated to the language you know, and it is spoken out by a text-to-speech system. This pipeline is very useful, very popular as an assignment or as a project. So try doing something on this and choose your own language. Okay. So OCR, machine translation, and then text-to-speech. Then physics-driven natural language processing. So the class is very diverse. I think I have seen there are people from physics, chemistry also. Now, physics-driven NLP is application of chaos theory, for example, and the implementation of this chaos theory to demonstrate emergence of language. Okay, how do children begin to produce language? Initially, everything is so topsy-turvy, so haphazard, but gradually an order begins to emerge. So, physics-driven NLP has this question in mind. Maybe some of you will be challenged and enthused to work on this problem. I'll be very happy if something comes out of this project. Then hybrid of statistical and neural systems in low resource scenarios with applications. Low resource scenarios, the problem is you do not have enough training data. And when you don't have enough training data, neural network based systems are very low performing. Okay, but statistical NLP systems are not hungry for so much data. So can you have a combination of statistical and neural systems and then address this and then address the task? So this is hybrid of statistical and neural systems, and then anything that you find interesting, anything. Okay. In NLP, there is no dearth of idea. There is dearth of data and dearth of compute research, as you know. So this is the project plan, and for project plan, I forgot to give the timeline. You should off and on meet the TA team. We'll make an assignment. We can make a. No. What we'll do is that we'll assign TAs for a group of students. So you have to keep meeting them, discussing our ideas, discussing the work that we're doing, and then we progress on the project. Project cannot be done in 1 or 2 nights. Okay, you have to keep working on this continuously. And you'll really enjoy it if your project is successful. And I'm also happy to tell you that every year, 1 or 2 papers have come out of this course and the next course that I teach, CS626. Okay, so assignment and project. Any question on the project plan? Yeah. You have to give a demo. And you have to give, also have to make a presentation. The slide formats will be shared with you. And for all these assignments, the slide formats will be shared. Okay, so we were discussing NLP layer. And today let us deep dive into one specific topic. That topic is part of speech diagrams. Okay, this is a task which needs to be solved. Why it needs to be solved, we'll see very soon. But let's get the definition of the problem. I have also decided that from this class onwards, we'll have a 5 minutes break after 45 minutes. Okay, around 45 minutes. And please come back to the class after that. And then we'll also finish. And we'll also finish the class 5 minutes before, because I believe there is a large class like mine at 7 o'clock. I think it is a machine learning course. So we'll finish 5 minutes before. Okay. The effective number of minutes in the class will be about 75 minutes, as I see. So part of speech tagging. So the problem is this. Words are divided into different kinds of classes called parts of speech. Okay, this you have heard, you have read it in the school. There are different parts of speech. There are 8 parts of speech: noun, adjective, pronoun, verb, adverb, preposition, conjunction, and interjection. They are also called the grammatical categories. Now, This is the part-of-speech hierarchy. Part-of-speech is divided into content words and function words. Content words are of three kinds: qualifier, noun, and verbal. Qualifiers are two kinds: adjectives and adverbs. Adjectives qualify nouns and adverbs qualify verbs. Okay, runs quickly. Quickly is an adverb. Function words are again three kinds: adposition, conjunction, and exclamation. Under adposition, you have preposition and postposition. Okay, languages where the word goes to the end, like in Hindi, you do not have preposition, but you have postposition. Okay, chammach se khana khaya. Se comes after chammach, but with spoon, with comes before spoon. So preposition, postposition, distinction. So there is a part of speech hierarchy, and it is very useful and fundamental. Then there are two methods of classification, which is syntactic and semantic. We'll come back to those nitty-gritties little later. Let's have the problem statement first. We have to input a sequence of words, and the output will be a sequence of labels of these words. So this is a sequence to sequence mapping problem. Okay? And sequence to sequence mapping problem is a very fundamental problem in whole of AI. Okay. One of my favorite examples is if you have a surveillance, AI-based surveillance system installed in an airport, let's say, or in a train station, and you have a sequence of movements of a person. The person walks in, okay. Then let's say bends, places a bag, gets up, and then walks away. So this sequence of movements, can this be classified as suspicious activity? Is the person planting a bomb or something? Okay, this is a very important problem for any surveillance system, and AI-based computer vision assisted surveillance systems have to label a sequence of video frames. Okay, which finally has to be classified as into binary into a two-class problem: benign or suspicious. Benign means ordinary, no problem, routine activity, or suspicious. So you have lots of training data of this kind of video frame, and they are labeled as benign or suspicious, and you run a classifier to classify it. For a new situation where the video frames have been captured, you will have to give this label. Okay, so sequence classification and sequence to sequence mapping is extremely important problem in whole of AI. So the output will be a sequence of labels of these words. Now, while you are doing part of speech tagging, you are actually getting yourself skilled in any kind of sequence to sequence mapping task. Okay, part of speech tagging happens to be the simplest of sequence mapping tasks, and extremely good for educational purposes. So input and output is clear. Now, the reason why this problem is difficult is that words typically have multiple parts of speech. So which part of speech is applicable in that context? Okay, it is also called in-context learning. Okay, in that context, what tag is applicable? That has to be decided from the context. For example, if you take the word close, close has all parts of speech: adverb, adjective, verb, noun, all major parts of speech. Okay, so running close to the computer is adverb, close as escape is adjective, close the door, verb, and towards the close of the play, noun. Okay, it has all the parts of speech. So disambiguation can happen only from the context. Now, if the sentence is who is the Prime Minister of India, then who will get this label WP? This is called who pronoun. Is gets the label VZ, auxiliary verb. The is DT, determinant. Prime is JJ, adjective. Minister is NN, noun. Of is in, preposition. India is NNP, proper noun. Question is punctuation. So these labels come from a repository called Penn Tree Bank repository. I'll describe them moving forward. So you have these labels, and for every position or for every word, you will have to choose that label. And the reason why it is difficult is that for every word, multiple parts of speech are possible. You have to choose one amongst the many possibilities. Okay, so this is the input-output scenario. Now let me describe the machine learning based part-of-speech tagging. One might question why machine learning is needed for part-of-speech tagging. We'll describe why machine learning is needed, and also we have a new book. Me and my student Aditya Joshi, who passed out quite a few years back and now is a faculty member in Australia. So we have written a book which came out last year, and I believe the part-of-speech tag chapter is written very well. Okay, so why machine learning is needed for part-of-speech tagging? You might want to look at that chapter and the discussion there to understand why machine learning is needed for part-of-speech tagging. And you can possibly see that any disambiguation is essentially a machine learning problem. Any disambiguation requires classification, and classification we know is a machine learning problem. Okay, so let me introduce the framework, and after this we'll take a 5-minute break. So this framework is called the noisy channel framework. It came from automatic speech recognition. So the input is a word sequence W, and the output is a tag sequence T. Okay, people love NN and BB. So we would like to get that possible that tag sequence, which is the best for this input sequence. Now, what does best possible mean? It is a probabilistic expression. We choose that tag sequence given the word sequence for which the conditional probability PT given W is the maximum. Now, argmax computation, I think many of you have seen. Those of you who have not seen argmax before, make sure that this is properly absorbed by you. Both argmax and max, both the functions, compute a maximum value. Okay, argmax returns x, max returns y. Y is equal to fx. Okay, argmax will return x for which y is maximum, and max will return y for which y is maximum. Okay, so argmax of over t for probability of t given w is returning t star, which is what you are interested in. Okay, this is the framework. Now we break probability of t given w into two parts, applying Bayes theory. Okay, so this is the probabilistic formulation of our problem, and we are interested in this probability value, probability of t given w. Now place yourself in the situation of thinking how a new sentence will be POS tagged. Okay, suppose I give you a new sentence, and this needs to be POS tagged. So let's say the sentence is the sun is shining. The sun is shining. So in this case, the part of speech the tags will be the is DT, sun is NN, noun, is VZ, auxiliary verb, shining is the main verb, the verb is in ing form. So this is VG, let's say. Okay, so 4 words, 4 labels have to be given. And we have decided to take the probability path. Okay, probability path. So given the sentence, one thing we can do is that we can enumerate all possibilities. Okay, so suppose every tag, suppose the tag set, tag repository has, let's say, 40 tags. Suppose, okay, and in absence of any other knowledge, we would like to say that any word can take any of these 40 tags. Suppose we are working with a uniform probability distribution in our mind, a system of complete entropy or uncertainty. We know nothing. Okay, And we know, we just know that the POS tag repository is not arbitrary. It has 40 possibilities. And any word can take one of these 40 possibilities with uniform probability. So then given these 4 words, the sun is shining. How many, what is the size of the search space? Please don't talk. Please don't talk. Please don't talk. What is the size of the search space? The first position can be filled in 40 ways. Second, third, fourth. So 40 to the power 4, which is an enormously large number. Okay, but that is not the main difficulty. The main difficulty is that I have to get the probability of each of these possibilities. We have to get a score for each of these. Why is it declining? I have to get a score for each of these. So let's say the sun is shining. I should get dt, nn, vz, vg. This sequence is my target sequence. That is what should emerge from my computation. And this should have the highest probability. Okay. So I want to get the probability of this sequence. Is it visible from the back? Okay. So I want the probability of this sequence. Let me be extremely sloppy. So what I know is that I can write this as probability of dt. Okay. So this is, yeah, dt given nn. This one? This one?
Yeah.
So nn here. I need to know this probability value. I need to know the probability values. Another way I could have done this is that I see in the corpus how many times this dt, nn, vz, vg appears. Okay, amongst all possible 4 POS tag sequences. Okay, right? So I can do that and compute that ratio to see that probability. Now the problem is that this exact combination of POS tags may not appear in the corpus. Okay, so this exact sequence may not appear in the corpus at all. Also, I have not written it correctly. I have to say that this is conditioned on the sentence here. Okay, it is conditioned this sequence has a conditioning part which is the sun is shining. Okay, this is a little more accurate one. this probability table. So it seems I can first call these W. If I wanted to compute this expression directly without going to what is this rule called? Does this step from this step, what rule are we applying? This is the chain rule of probability. Chain rule of probability. So I could compute also without going through chain rule by finding out the number of times this sequence appears with this input sequence. Okay. Divided by the number of times this sequence appears with anything. Okay. Or the number of times this sequence appears in the corpus is in the denominator. And the number of times this sequence appears with this constant sequence in the numerator. Are you with me? So this will be, if I do not apply chain rule, this will be equal to number of times this sequence T star appears with W divided by number of times W appears. We'll see how many times the sun is shining appears in the corpus. Recorded here. And how many times the sun is shining appears with this tag sequence. If this combination is the highest, then I'll output this tag sequence as my result. You immediately see various problems, right? This will not work. What is the main problem? That is not work. So the corpus, this sentence will not be there in the corpus. This is a new sentence, and it is not there in the corpus. If the corpus is small, there is very high probability this is not there in the sentence. If the corpus is extremely large, infinitely large, then it appears. And that is the strength of LLMs, no? LLMs take, huge context as the conditioning part. And they're lucky to have enormous amount of data over centuries and centuries of, speech, text, which have been digitized. And now it is very visible that the training data has exactly this combination. Okay, and this probability is computed without any difficulty. But in a practical situation where the corpus is small, this sentence can be a new sentence. And so this whole computation is not possible. This is the difficulty. What is the way out of the difficulty? Yeah. Yeah, sorry. Oh, no. Oh, good point, but no. Okay, so very good point. So this question is, if we jumble the words, can the tag sequence remain same? But how does it help? Hmm? I can't hear you properly.
The sentence will become meaningless. Or
Who is worried about meaning? I'm at the lowermost, almost the lowermost level of the NLP stack. Meaning is at the highest level. Maybe data. No. This is not the right argument. The Chinese ambiguity. So we get ambiguity between Chinese. What ambiguity? No ambiguity. If in the next sentence it is no. So wait. So for you to think about and a word appearing in the beginning of a sentence and at the end of a sentence and in the middle of a sentence can have different parts of speech. Yeah. So the way out is the way out is Markov assumption. I do not get the whole statistics. Okay. I do not get these statistics. These particular statistics I don't get. These things are called statistics, right? Given the data. So I do not get this combination as such. I do not get these sequence of words also as such. But I can get the parts in the corpus. Please don't talk. Please don't talk. So, but I can get the parts. I know that the is very frequent in the corpus. I can get the statistics of the from the corpus. The sun is also likely to be extremely frequent in the corpus. Okay. E shining is very likely to occur in the corpus, even a reasonable size corpus. 1 million size corpus or 10 million size corpus, very likely to have this sequence. If it does not have, then I will make use of similarity. The sun is not present, but the moon is present. Now, sun and moon are part of speech-wise, even meaning-wise similar. Okay, so that takes us to what is called the continuous space. Sun and moon in the symbolic space have no similarity. They are spelled differently. S-U-N, M-O-O-N. The only character common is N. But they're semantically similar. If your word captures semantic similarities, word embeddings. And that's a different discussion. Okay, so I can get the parts and their statistics. And therefore, now let me try to see how to work with the parts. So that is where the chain rule is helpful. Okay, so I apply the chain rule of probability and get the parameters in this shape. Earlier, my parameter was this whole expression. Now the parameters are in this shape. Probability of dt given W. So one would come back and ask, what problem have we solved really? We say that W is not in the corpus. So what exactly are we doing? I'm trying to divide and count. Okay, I break the sequence into small elements, and the smaller the element, higher is the probability of getting that probability from the corpus. Okay, but you have to do something about W also. You have to break W also. Okay, so that is facilitated by the application of Bayes theory. So let us see this way. But before that, you see probability of dt and probability of n given dt. You see that we are talking about some kind of transition. Probability of n given dt. Ignore w for the moment. Probability of getting n in the next position, given the current position in dt, is a transition phenomenon. Okay, and the probability of n given dt is a transition probability. Similarly, probability of Vz given dt and n. If I ignore dt and it has to be probability of Vz given n, again a transition probability. And the reason why I'm trying to ignore dt is through Markov independence assumption. The Markov assumption is saying that the level at the position, the tag at the position, depends only on the previous position. Okay, so this becomes a transition probability. What to do with W, we'll see. But you see the thought process. Okay, how gradually you are progressing towards a manageable situation from the data. Okay, that's why I said that a student of NLP must understand statistical postulating and implement also to be motivated by the thinking process. And where did this thinking process come from? It came from automatic speech recognition, ASR. It came from automatic speech recognition. We'll talk about it very soon. Okay, so see, gradually we are able to deal with smaller number of random variables, and they can be computed from the data. The headache still remains, namely the appearance of W in the conditioning part. Okay, so to break anything in the conditioning part is not easy. So those of you who understand probability well, have done probability course, like probability, do you know how we can break a random variable into smaller parts, which appears in the conditioning part, not in the conditioned part? How do we break it into small parts? By bringing the random variable in the conditioning part to the conditioned part. Okay, and then apply chain rule. How can you bring a conditioning random variable to a conditioned random variable? Bayes theory, Bayes rule. Bayes rule. Okay, so let's see the formulation now on the slide. The mathematics of part-of-speech diagram. So we are interested in the best possible tag sequence, which is called T star. And that's equal to argmax over T, probability of T given W. Okay, this is exactly what we wrote here. Now I can apply Bayes theorem and write probability of T given W as probability of T into probability of W given T. Okay, over all possible T. Now there is a denominator here. Probability of T into probability of W given T should be divided by probability of W. That is the Bayes theorem. Okay. Bayes theorem is probability of T given W is probability of T into probability of W given T divided by probability of T. But probability of W. But probability of W can be eliminated. Okay. The reason is that my variable of interest is T. T varies. Okay. And the scoring varies because of T. As T changes, I get a different score in terms of the probability value. Okay. And probability of W being in the denominator has only division by a constant effect. And we are interested in the ranking of these probability values. If the denominator is same for all possibilities, then it can be ignored because I'm interested only in the maximum probability value. So PW drops. Okay. See that. Those of you who are seeing it for the first time, make sure that you understand why probability of W does not appear in the expression. Okay? Because it comes as a denominator and as a constant with respect to T. Now comes the independence assumptions. Probability of T is nothing but probability of the whole tag sequence. This tag sequence. Probability of T is probability of this tag sequence. Now apply chain rule. Probability of T is written as probability of T0. T0 is a fictitious random variable. It indicates the beginning of the sentence. Probability of T0 into probability of T1 given T0, the tag at position number 1, the first word in the sentence. Into probability of T2 given T1 T0, probability of the tag in the second position, and so on up to probability of Tn plus 1. Tn plus 1 is the sentence finisher. So the sentence beginner hat and the sentence finisher dot play a very important role for part of speech diagram. So the Tn plus 1 is dot, T0 is hat. So if the sentence has n words in it, then the sequence we are dealing with is n plus 2. So probability Tn plus 1 given Tn minus 1 up to T0 is the last expression. This is absolutely correct because it obeys the rule of probability. This is chain rule of probability. The next expression will be probability of T0 to probability of T1 given T0. Here comes the Markov independence assumption that T1 depends only on T0 and nothing before this. So the tag at any position depends only on the previous tag and nothing else. So proceeding this way, we have probability of T2 given T1 and finally probability of Tn plus 1 given Tn. So this becomes a product of probability of Ti given Ti minus 1. I varies from 0 to n plus 1. Okay. So we have a product of transition probabilities from tag to tag. Any question? You agree with the formulation? Yeah. So this is also an important question. It will be relevant to your assignment. So will you count capital THE because the is appearing in the beginning of the sentence and small THE which appears in the middle of the sentence? Will you count them as same tokens? The word used is token. So what is done is that when you do part of speech tagging, you make all tokens with small letter. So capitals are turned into small letters and they're counted in the same basket. Okay. Yeah.
Can you show that the part codes for each and every say a sentence or each and every group of?
Yeah. So Markov independence assumption doesn't hold in all cases. Okay. Now, so this is the quarrel between phenomenon and modeling. Just wait, let me finish this. Does F equal to M hold universally? Well, let me fail. When mass is not constant. And when is mass not constant? Very close to the speed of light. Right? So this is the classic quarrel between model and phenomenon. Okay, we are trying to model a phenomenon. The phenomenon is the influence of the part of speech at a position by the part of speech around it. So it doesn't hold. In fact, it fails quite badly for words in disambiguation. But for part of speech tagging, the Markov independence assumption is very effective. Because the disambiguation of a part of speech can be done from local information. Okay, from a very small neighborhood, you can collect the information and disambiguate a part of speech. Yeah, yes, yeah. Probability of T0 is always 1. Yeah.
But it can be
Oh yeah. So that's why it is an assumption. The probability of a tag at a position can depend on many things. Well, that is true about the mathematical world, but the linguistic world does it actually depend on many things, or is it most of the time determined by the previous tag? In fact, empirically, it has been found that for English, trigram assumption is very good. Okay? The part of speech tag of a word at a position is almost completely determined by the previous two part of speech tags. Okay? So the first parameter we have dealt with, which is PT. Now, probability of W given T. W was a real headache, if you remember. Okay, because there is a new sentence, and it is very unlikely that this will appear as such in the corpus. So I have to break this into small parts. So is the whole class with me on this? But a lot of talk going on. Please. Second last bench, please. Why so much of talk? So just this one. So are you with me on this point that if you want to compute the statistics of a large object, which means a long sentence, you can get the probability approximated by the probability of its parts. You break it into smaller parts. The way to break into smaller parts is chain rule of probability. And taking the smaller parts, making them practical is Markov independence assumption. So this combination of chain rule and Markov independence assumption is sacrosanct in machine learning and NLP. Yeah. Why did we need Markov assumption? Because this long sequence probabilities you cannot compute. There is no evidence in the data most of the time. Okay, now what to do about the next part, and then we'll finish the lecture today. The next part is probability of W given T. Now, probability of W given T, you cannot compute as such from the corpus. In the general case, most of the time we cannot compute, except in the era of large language models. large language models have so much of corpus and so much of, previously done language-based tasks that it has ingested everything. I'll not be surprised if the sentence is that the sun is shining. It will be there. The sun is shining. This sentence will be there in the training corpus of GPT-4. I'm sure. And I'm also quite sure that the tag sequence of this sentence has been found by somebody. Okay, maybe some professor in, let's say, University of Minnesota. He or she might have exactly done this. She or she said this in the class. The video was uploaded, the lecture was uploaded. It went into the training corpus of GPT-4. Absolutely. And now it doesn't have to be computed. Computer probability, that is also very interesting. It computes this through softmax. Yes, we remarked this in the first class. Yeah. So all this is very good. So PW given T, I apply again chain rule. Probability of W0 given T0 to Tn minus 1. The whole T is T0 to Tn plus 1. And what is W0? W0 is a sentence beginner, the hat symbol. So please remember these two guardrails for any sentence. The sentence beginner hat, the sentence finisher dot. They're always there. Okay. So probability of W0 given T0 to Tn plus 1 into probability of W1 given T0, given W0 and the whole tag sequence. Probability of W2 given W1, W0 and the whole tag sequence. Finally, probability of Wn plus 1 given W0 to Wn and T0 to Tn plus 1. All this is following systematically from the laws of probability. There is no surprise there anywhere. No assumption also. Now we apply an assumption. The assumption is this, and this is where linguists have a lot of problems. They find this assumption extremely non-intuitive. So the assumption is that this whole exact expression is approximated as probability of W0 given T0. The assumption is that a word is determined completely by its tag. This is inspired by speech recognition. So the word is completely determined by tag. What does this sentence mean? Not understandable by common sense. A tag is determined by the word. What do you mean by a word determined by tag? Okay, so this is completely mathematical thinking. We are making use of an algorithmic and mathematical thinking here, leaving out the common sense language phenomenon. Mathematically, this is fine. And it allows me to compose an algorithm which can be implemented by hidden Markov models, logistic regression and so on, or by a neural network. And it delivers the result. Okay, given a new sentence, I can give you a satisfactory tag sequence most of the time. That is the probabilistic approach. So now we look at the derivation. Probability of W0 given T0, probability of W1 given T1, probability of Wn plus 1 given Tn plus 1. And this is the product of probability of W given T at all positions. So these probabilities are my second set of parameters. These are called lexical probabilities. And the probabilities which we saw in the previous slide are transition probabilities. Now, if I look upon the words, okay, as observations, because the words are in front of me, they are the observations. And if I look upon the tags and states which are hidden, and they have to be uncovered, the state sequence has to be uncovered, the tag sequence, then we have directly fallen into the framework of hidden Markov model. Hidden Markov models have transition probability and they have observation probability. The observation probability here becomes the lexical probability or the words probability given the given this tag, given the state, and we are now good to go with a technique which is well known. This is hidden Markov model. Okay, is the whole sequence of thinking and depiction clear to you? I ask that you read that chapter on counter-speech tagging in our book. Okay, so this is the final expression, and then when we put this together, we have an automaton of this form. The automaton is this. I have the observation hat at the beginning of the sentence, and I have a state also in the beginning of the sentence, which is again hat. Then I have the state sequence, the state as N or V, corresponding to the observation people. The sentence here is people jump high. So people can be noun or verb. Then jump can be noun or verb. This was a good jump. People can be noun or verb. People can be verb when we say the town was peopled by soldiers. Then high can be adverb or adjective. Okay, high can be noun also. So all these possible tags are documented for every word, recorded for every word. And then finally, I have the ending of the sentence, which is dot, and that corresponds to the dot state also. And everywhere, you see, I know the parameter values. I know the weight of the connection from hat to n, because this probability of n given hat, this is equivalent to asking what is the proportion of sentences which begin with n. Would you say the probability is 1? What would you say? Will the probability be 1? Probability of n given hat, is it 1? Why is it not 1? Not all sentences begin with noun. And what this thinking is a linguistic thinking. There is a phenomenon. We observe that not all sentences begin with noun. Okay. So this probability of n given hat, I know if I have corpus, annotated corpus. So everything is pointing to data, where we have words and the corresponding tag, and therefore it is good for me to show you very quickly, and we will elaborate this later, very quickly, the data, okay, which is at your disposal and from which you can get the statistics. So the most famous data is Pen 3 lamp. You will have to make use of that for your assignment. Then universal dependencies, British National Corpus, Brown Corpus, these are all for English. They actually heralded or introduced statistical natural language processing. So the importance of these data sets is enormous. As a historian of NLP or student of NLP, you appreciate this point. Tiger is a corpus for German postgrad. CONNL 2000 is the data you will use for your second assignment. Then Ontonodes is an extremely rich data because it has POS tagging as well as other kinds of linguistic annotation. Google Universal POS tags is a little more recent. Dataset with POS tags for various languages derived from the web data. And only Google could do it, right? Who else could do it? They have the advantage. They are the search engine maker, so they have the whole web at their disposal. So they also benefited the community, and they did not sit on it. They created this data set and gave it to the community for part of speech learning. Then GAM is the Georgetown University multi-layered anyway. Treebank 3 is extension of Treebank. This is our contribution. B is IS tag set and data set. So Indian languages also needed POS-tech corpus. So many groups from India, included IIT Bombay also, designed the POS-tech as well as dataset. Children's is a large collection of corpora for the study of first and second language acquisition. And so on and so forth. This corpus is very famous. Switchboard DMSL is used in ASR as well as POS-tech, and so on. So we'll continue this discussion on Thursday, and please start thinking about the assignments.